This video is brought to you by mywayteaching.com.
In this part, let us solve one more simple problem. The flow rate of water from a tap of diameter 1.25 centimeter is given by 0.48 L per minute. The coefficient of viscosity of water is 10 raised to minus 3 Pascal second. After some time, the flow rate is increased to 3 L by minute. So characterize the flow for both the flow rates. This is the problem. So let the speed of flow be V and the diameter of the tap be D. So that is given by 1.25 centimeter, the diameter of the tap, and the volume of the water which is flowing out per second is given by V into pi d square by 4, where we can get V is equal to 4q by d square pi. So we then estimate the Reynolds number, that is given by 4 rho q by pi d eta. This is the Reynolds number, which is given by 4 into 10 raised to 3 kg per meter cube into q. The value of pi is 3.14 into 1.25 10 raised to minus 2, and eta is 10 raised to minus 3 Pascal second. It is given. So we'll get the value as 1.093 into 10 raised to 8 since initially it is given by 0.48 L by minimum. We'll write it in terms of the meter cube, that is 8 into 10 raised to meter cube per second. Okay, and we obtain the value of Reynolds number as 815. Since this is below 1000, the flow is steady. So when we consider Q is equal to 3L by per minute, it is given as 50 centimeter cube per second, that is given by 50 into 10 raised to minus 5. So in this case, we get the value of Reynolds number as 5095. So this will be turbulent since it is greater than 2000. So now let us study what is surface tension. See, you must have noticed that even oil and water do not mix. Water wets you and me, but not ducks. Mercury does not wet glass, but water sticks to it. Oil rises up a cotton wick in spite of gravity. Sap and water rise up to the top of the leaves of the tree. Hairs of a paintbrush do not cling together when dry and even when dipped in water, but they form a fine tip when taken out of it, isn't it? So, all these and even many more such experiences are related with the free substance surfaces of liquids, which means the liquids they which having no definite shape, isn't it? But they have a definite volume. They acquire a free surface when poured in a container. So these surfaces possess some additional energy. That phenomena we call it as surface tension. Okay. Now let us study the energy which is associated with that surface. A liquid stays together because of attraction between molecules. One molecule will attract the another molecule so that that liquid stays together. You just consider a molecule which is well inside the liquid. The intermolecular distances are such that it is attracted to all the surrounding molecules. You can see that in this figure. Okay, the intermolecular distances are such that it is attracted to all the surrounding molecules. So you can see here it is attracted to all the surrounding molecules. This attraction results in a negative potential energy for that molecule, and it also depends on the number as well as distribution of molecules around the chosen one. But the average potential energy of all the molecules is same. So that is supported by the fact that to take a collection of such molecules and to disperse them far away from each other in order to evaporate, the heat of evaporation required is very large. For water it is about 40 kilojoules per mole. Okay, you just consider this one figure, a molecule which is near the surface. Only lower half side of it is surrounded by the liquid molecules. Here, this upper it is free. So there is some negative potential energy due to this, but obviously it is less than that of a molecule in bulk. So that is the one which is fully inside. So approximately it is half of the latter. Thus, molecules on a liquid surface have some extra energy in comparison to the molecules in the interior. So these molecules have some extra energy compared to the liquids which are molecules which are completely immersed. A liquid thus tends to have the least surface area which external conditions permit. Increasing surface area requires energy. Most surface phenomenon can be understood in terms of this fact only. Okay. Since liquid consists of molecules which are moving around, they cannot be perfectly sharp surface. The density of that liquid molecules it drops rapidly to zero as we move along the direction which is indicated in this figure C. Okay, in a distance of the order of few molecular sizes. So now let us study surface energy and surface tension. Okay, see, energy is associated with surface of liquids. The creation of more surface keeping other things, which means like volume, it requires additional energy. For that, you just consider an horizontal liquid film ending in bar free to slide over parallel guides. Okay, this is an horizontal film. Suppose that we move the bar by a small distance d. Okay, we move that bar by a small distance d. Since the area of the surface increases, the system now has more energy. This means that some work has been done against an internal force, so that internal force is represented with F, and the work done by the applied force is F into D. Internal force is F and the work done by the applied force is F into D. And from the conservation of energy, this is stored as additional energy in the film. If the surface energy of the film is S per unit area, then the extra area we call it as 2dL. Okay. A film has two sides and the liquid in between. So there are two surfaces. So the extra energy is. So this quantity S is the magnitude of the surface tension. It is equal to the surface energy per unit area of the liquid interface, and it is also equal to the force per unit length exerted by the fluid on the movable bar. Okay. So far we have talked about the surface of one liquid. Just more generally we need to consider fluid surface in contact with other fluids or in contact with solid surfaces. So the surface energy in that case, it depends on the materials on both the sides of the surface. For example, if the molecules of the materials attract each other, then the surface energy is reduced, while if they repel each other, the surface energy is increased. Thus, more appropriately, the surface energy is the energy of the interface between the two materials and it depends on them. So, we make the following observations from the above. The first one is surface tension is a force per unit length acting in a lane of the interface between the plane of the liquid and even any other substance. It is the extra energy that the molecules at the interface have as compared to the molecules in the interior. Okay. And the second point is at any point on the interface besides the boundary, we can draw a line and imagine equal and opposite surface tension forces S per unit length of the line acting perpendicular to the line in the plane of the interface. So the line is in equilibrium. To be more specific, you just imagine a line of atoms or a molecules at the surface. The atoms to the left pull the line towards them, those to the right pull it towards them. And this line of atoms is in equilibrium under tension. So, if the line really marks the end of the interface, as in previous cases, there is only force S per unit length which is acting inwards. Okay. This table shows the surface tension of some liquids at the temperatures indicated with the heats of vaporization.